So these are different categories in ARM instruction set. We are going to work with a processor. Name is ARM7 TDMI. ARM7 TDMI. This is the processor name. ARM7, this belongs to family, this 7 number. This is belongs to family. In version 4, it belongs to version 4. And what is T? T stands for thumb instruction set. It supports thumb instruction set also, which is of 16-bit width. So I said ARM is a 32-bit processor. It also has a 32-bit instruction set. Every instruction is of 32-bit width. When I come with in its nomenclature, letter T means apart from 32-bit instruction set, it also supports a 16-bit instruction set. The advantage of thumb instruction set is high code density. So in place of one 32-bit instruction set, instructions, I can now load two instructions which are of 16-bit width. Okay, in place of one instruction, if I am using thumb instruction set, I can load two instructions. Okay. So with this advantage, I could achieve 33% of high code density. As there are even certain limitations are there even in thumb instruction set. Right, that is about a T-bit. And next D. D stands for JTAG debugger. JTAG debugger. Through JTAG connector, you could able to observe what is happening inside the CPU while executing your program. Okay, you can observe your registers and memory locations using JTAG debugger. And next M stands for fast multiplier. Fast multiplier. So as data is also 32-bit width in ARM processor, when I perform a 32 by 32-bit multiplication, I need certain time. Each bit need one clock cycle. So to perform a 32 by 32-bit multiplication, more number of clock cycles are needed. That can be reduced by using a fast multiplier, which will be doing up to 64-bit your output, or else if you need only lower half of your result, which is 32-bit width within one clock cycle. That is the advantage of fast multiplier. And next I stands for in-circuit emulation. By using this, you can create breakpoints and watch points while the program is executing in the CPU through in-circuit emulator without, when we come for embedded system, without removing the chip from your board, you can able to simulate that, emulate that. You can able to observe how your program is executing, where your CPU is moving from one instruction to another instruction, what is happening there, everything you can observe using this in-circuit emulation, which helps you the debugging, fixing the errors while the program is executing within no time. That's the advantage of ICE in-circuit emulation. So this is the type of processor that we are going to see further. And the corresponding ARM instruction set for ARM7 family is categorized into 5 groups. One group related to data processing instructions, another branch instructions, load and store instructions, software interrupt instructions, and PSR, program status register instructions. Okay, we'll see one by one. The first category, data processing instructions. Name it says it performs certain operations on the data. Let me move to next slide. These are data processing instructions related. And this diagram, if you remember, this is the basic data flow model of your ARM family, right? So coming to data processing, which includes all arithmetic, logical, comparison, and data movement related instructions. Okay. Before going to these instructions, let me explain the basic instruction format for ARM processor. So you already know what is the basic instruction format for Intel microcontroller, that is 8051. So past 3 units we have studied completely about 8051, its architecture, instruction set, addressing modes, programming capabilities, on-chip and off-chip peripherals, and their programming both assembly and C. Right now, we are going to learn another processor, that is ARM7, which is based on the 32-bit instruction set. So as it belongs to different manufacturer, different family, different designers, so it also has different way of programming. Okay, so the syntax in assembly language with respect to ARM, if we see, it is different. Mm, uh, when we come for syntax, it has several fields here. The first field, the operation code. Indirectly, it means the operation code. What is the operation to be performed? Uh, and then we have another field called conditional code. Conditional code, this one. Wait. Okay, so this is the next field, conditional code, which is available in flower brackets. So it means it is optional one. As I have already mentioned, what are the deviations of ARM processor from RISC characteristics? One of the deviation is this conditional based execution. Every operation can be performed based on a condition. Here you can mention a condition. We have around 16 different conditions which are based on the flags available in ARM processor that we have seen. The format of CPSR register, CZNV, 4 mathematical flags are available. Each flag, it can be 1 or 0. If I have a carry can be 1 or a 0. Similarly, a 0 flag, it can be 1 or 0. Similarly, overflow flag, it can be 1 or a 0. So likewise, we will be having different conditions, not only one flag. A combination of the flags can also be specified as a condition. So up to 16 conditions are available, right? That condition can be added after each opcode, which is executed whenever the condition is satisfied. If the condition is not satisfied, it is considered as just a no operation. The instruction will be skipped. Nothing will be performed. Without involving branch operations, these conditional based execution will do the needful. That is the biggest advantage in ARM processors. Pipeline will not be affected every time. Okay, it not be frequently affected because of the branch operations. We are reducing using branch operations with the help of conditional execution. Okay, that's the optional field. If nothing condition is mentioned, it is considered as AL, as always the opcode will be executed. Okay, and the other optional field, which is called S, stands for save the status. Flags will be affected or not for the specific operation is given by a specific letter called S. With your opcode, if I have added letter S, then the flags are affected. If I haven't added S, then flags will not be affected. Normally in 8051 instructions, if you see addition followed by 2 registers, if I say, mm, it's a basic arithmetic and logical operation. Obviously, the flags will be affected in PSW. But when I come for ARM7, you have an option to affect the flags or not to affect the flags by using this extra letter S. Okay. So these are the optional ones. Okay. If you haven't mentioned S, flags will not be affected by default. That is about ARM opcode. And next, ARM processor uses 3 operand instruction field, not just 2 operands, unlike Intel controllers or processors. Okay, so the first field is at the destination register, which is considered as a RD, and the second field is RN, one of the register in your register file structure, and the third field is the operand, which is have multiple options. Your operand 2 can be given directly from the register file. It can be a simple register, or it can be an immediate value, or it can be a register which is scaled or traveled through barrel shifter, a shifted version of your register. These are the 3 options available for operand 2. Right? It can be a direct register, or it can be an immediate number, or it can be a register which is shifted by using barrel shifter. Okay, these are the 3 options for your operand 2. So this is the basic instruction format for ARM7, right? So with this format, let me introduce the arithmetic operations. So these are arithmetic operations. Add ADD, it's a simple by observing the letter itself. It is clear. ADD stands for addition. Okay, we want to add 2 registers, and the content should also be copied into a register. That is clear because ARM is particularly using load and store architecture. You can perform operations only on the registers. You cannot perform direct operations on the memory, right? See, when I want to write a simple instruction using addition, so my instruction will be like this. Okay. So my instruction is add space. I'm using R0, R1, R2. So it means that I want to perform operation of addition between R1 and R2 and load the result into R0. Okay. So this is the meaning of this instruction. Add means. Okay. So, basic arithmetic operation, it is you are by default expecting the flags to be affected. If I get any carry out of this addition, I want to affect the carry. If my result is positive, I want to affect my negative flag. If my result is 0, I want it to affect the 0 flag. If my result is overflow, assuming the numbers are signed operands, then overflow flag will be affected. Okay. So, but your ARM processor, as I mentioned, this simple add will not affect the flags. If I want to affect the flags, you have to add the letter S to the opcode, right? This is my opcode, and this is the extra letter added, which confirms the saving of the status, nothing but CZNB flags in CPSR by using the letter S. Okay, if I have mentioned S, then only the flags are affected in CPSR register. N, Z, T, P. These 4 flags will be affected. Otherwise, the flags will not be affected. Okay, so that is about addition. Similarly, ADC stands for addition with the carry. Okay, so ADC stands for addition with carry. So apart from just adding your addend and agand, it also add with the carry. Carry is also added. That is what ADC. And S is there, so flags will be affected. And now SUB stands for subtraction. So when I use subtraction, SUB, so first operand, from that second operand is subtracted. Okay, so this is how it is doing. SUBS. R1 minus R2 will happen, and the result will be copied in R0, and also the flags will be affected. Okay, so that is, since I have added S here, the flags will be affected. If you remove S, the flags will not be affected, right? That is SUB. Next, SBC stands for subtraction with the borrow. It is actually, okay, subtraction with the borrow means it is performing the subtraction with the borrow. Minus borrow you have to use. In case of ARM7, borrow is nothing but complement of your carry flag. Okay, so previous carry, complement of nothing but not of your carry. Borrow is not equivalent to carry in case of ARM7. It is complement of carry. Okay, because ARM7 uses 2's complement addition for subtraction, not just a binary subtractor. It is 2's complement addition. When you want to perform addition of subtraction of R1 minus R2, how it actually doing? It first perform 2's complement of 2's complement of R2, that gives me actually minus R2, right? 2's complement of R2 will gives me minus R2. This minus R2 is added to R1. Okay. So this minus R2 is added to R1 to get my R1 minus R. That's why the carry that we are getting is not the borrow. It is complement of the borrow. You can recall your DLD uh, digital logic design topics, two's complementation and their addition. If you recall it, you will get to know. While adding a two's complement number to another number, if I get a carry, it is considered that the result is a positive and we just neglect the carry. Okay, if I add a two's complement number to another number, while doing this, if I am not getting a carry, it is considered that the result is negative. Okay, right? So where if carry is 0 means the result is negative. When you get a result negative, because my first number is lesser than second number, then only my result will be negative. Nothing but to perform subtraction, I need a borrow. Okay, but actually here the carry is 0. So your borrow will be complement of the carry. That is what the consideration. ARM7 uses two's complement subtraction, not a simple subtractor. That's why your borrow is a complement of the carry. That's why it will be flags are affected accordingly. That you need to remember. That is what SBC. Next coming to RSB, which stands for a reverse subtraction. Reverse subtraction. Okay, so if I have used instruction like this, let us suppose. So if I use RSB R0 comma R1 comma R2, what it is doing, R0 is affected with the contents of R2 minus R1. So actually simple SUB means R1 minus R2 will happen. But when I have RSB, reverse subtraction will happen. From operand 2, operand 1 will be subtracted and it affects the flags if I add an extra letter S to it. Okay, flags will be affected if I add S. That is by default. Okay, so that is what reverse subtraction. Similarly, reverse subtraction with carry. Nothing but with borrow. Complement of carry have to be considered. That is about simple arithmetic operations. Okay, and next logical operations. Logical and logical or XOR and BIC, nothing but bit clear, can be done by using logical operations. And next comparison operations, you can compare two operands. Comparisons can be done on only two operands. It is not three operand instruction format. It just uses only two. I can compare only two numbers. So if I write an instruction like this, CMP compare R1 comma R2. So actually what is happening? R1 minus R2 will happen and the flags are affected. C, Z and B. Flags are affected but not the result of this subtraction. Okay. Subtraction result will not be affected anyway. Only the flags are affected. That's the operation of comparison which you are coming across for a while. Next, CMN, nothing but compare negative, means complement of your second operand is compared with your first operand. And test nothing but logical and operation between the two values and it checks for the result. And similarly, test for equality, whether the two operands are equal or not. That is another condition. It is logical and this is simple subtraction. And next, data movement. Move stands for just copy some number into another number, or else between the registers. If you want to do data transfer, then I can use move. And MBN stands for move negative. Negative of the first operand is copied into second operand. These two are also two operand instructions. Okay. So these are simple data processing instructions. Um, and let me have another important. This is about conditional execution. So simple add. Here there is no condition, so I should use the branch operation. But in case of ARM7, I have a conditional code like NE, not equal. If it is added, I can avoid this branching. That's the advantage. And these are the 16, as I mentioned, no, possible conditional codes. EQ, equal, not equal, carry set, or unsigned higher or same. Okay, this we will come across during signed comparison and unsigned comparison operations. Carry clear or lower. Minus, positive, overflow set, overflow clear. The equivalent condition flags are also shown here. When I am using capital letter means the respective flag is 1. Small letter use just the respective flag is 0. Equal EQ stands for equal, means the both the numbers are same. When I before this I would have used a compare instruction. The results are updated in conditional flags like this. So if capital Z means my Z is 1, it means both the registers are same. Not equal, then both the contents are not same, then 0 flag will be 0, which is given as small z. Z is 0. Carry set. Carry is 1, then capital C. Small c means carry clear. Capital N. Negative flag is 1, means the sign component is 1. Signed bit is 1. It says that the number is negative. If it is a small n, it is 0. It means the number is positive. Capital V overflow occurs, small v no overflow. And a combination of these flags are also given, which are widely used when we compare with signed and unsigned bits. Okay, so at the time of comparison, explanation of the program related to sorting of the numbers, then I will explain these conditional codes much clearer. These are the 16. And AL is nothing but always, which is unconditional. No flags will be checked. Okay. And you even need not to mention AL in your up code preceded. Okay. So it is by default considered as A. Okay. So for the next session, we'll start. I'll show how to program in assembly language for a simple arithmetic and logical operations. Okay. Right. So please join again after 15 minutes for lab session. Okay. So for the second session onwards, we'll start practical hours. Yes, am I clear? Yes, am I clear? Any doubts? Rejoin again after 15 minutes. 11:45. After 11:45 means 11:50 we will join.